And this one is problem 1.22. It says the light frame is hinged at A and B, and this is A and this one is B, and held up by a temporary prop at C. So this was a temporary prop here. Find the reactions at A, B and C when 8 kN load is supported at D, this one. So for the hinged here, if I start drawing the free body diagram, there will be 3 forces present, one in this direction, another one here, and another one there. Similarly at B also there will be these 3 forces, and at this support here there will be a vertical reaction this way. Okay, it's better for us to have a coordinate system in this case. So let's say this is X, this one is Y, and this one is Z. So now we can name these. So this is reaction at C, RC, and this is at A, so I'll call this RAX, this one as RAY, and this one as RAZ. Similarly, this is RBX, RBY, and RBZ. Okay, now all the distances in the X direction, they are 1.3 meter here, and in the Y direction we have these blocks which are 1 meter each. So now for equilibrium purpose, let's do the force balance, and from X direction forces we can get RAX plus RBX equals to 0. From Y force balance we get RAY plus RBY equals to 0. From Z we get RAZ plus RBZ plus FC has to be equals to 8 kN. Now let's look at the moment balance, and for this purpose we will do it about point A. Now about point A, RAX, RAY, RAZ, all 3 will not contribute to the moment. So the 3 points at which forces are present are your point B, point C, and point D. So total moment in this case, let's say the first point, which is point B, and we are going to use that R cross F for moment calculation. So with respect to point A, the position vector for point D is going to be 1.3 in the X direction and 2 in the Y direction, but negative. So we can write this as 1.3 I cap minus 2 J cap. This has to be crossed with the force that is present at D, which is in the minus K cap direction. So minus 8 K cap, and the unit here is going to be kilonewton meter. Now the next moment is at point C here. So the position vector for that is going to be 2.6 in the I cap direction and minus 3, because we have to cover this distance, in the J cap direction, and a force is your RC force with a positive K cap. Again unit is kilonewton meter. The last point here, which is point B, position vector for this is only 3.9 I cap, this crossed with, now there are 3 forces, so RBX I cap plus RBY J cap plus RBZ K cap kilonewton meter. Now all of these needs to be added together and equated to equals to 0. So now if I solve this from the first cross product, we are going to get 1.3 minus 8 I cross K and minus 2 J cross K. So this gives us 16 I cap plus 10.4 J cap. That's the outcome from the first cross product. Similarly from the second one, this one right here, we get minus 3 RC I cap and minus 2.6 RC J cap, and the last one here gives us minus 3.9 RBZ J cap plus 3.9 RBY y k cap equals to 0. Now this is a vector equation, so we have to collect all the I cap terms together, all the j caps together, and the k cap together. So from I cap equation we get 16 minus 3 RC equals to 0, and this gives us RC equals to 5.33 kilonewtons. From the second equation, J cap equation, we get 10.4 minus 2.6 RC minus 3.9 RBZ equals to 0. So with this, substituting the value of RC, we get the value of RBZ, which is minus 0.889 kilonewtons. And the last K cap equation right here is going to give us RBY equals to 0. Now going back to the force equations, since we have calculated RBY equals to 0, substituting this right here gives us RAY also equals to 0. Now we have calculated the value of RBZ here, so if I substitute it in this equation, this RC is also calculated. So if this is known, substituting these two values, the value of RAZ also comes out, and the value of RAZ is equals to 3.55 kilonewtons. So the only thing that is left is these two right here, and since there is only one equation, so it is not possible for us to solve this, so we call this indeterminate. And since there are no x forces, the only thing we can do is we can assume both of them to be 0.